2 minutes for you.
Because you're so slow.
Recording has begun.
It's not going to do anything to my computer.
And the computer's a reflection of the person. That's why mine is beautiful and messed up.
It was up the same.
And, I take back everything I just said.
What are you saying? We have the same idea.
We almost do.
Yeah, man, I love Lenovo's there. There's some workhorses.
Mm-hmm.
It's like a refurbished one too. Just slam it. Is it an XPS? Those suck ass.
For what?
Is it the XPS sucks?
They're great. They're great. They're beautiful. They're just messed up.
All right, so I'm going to review last week's workshop, and this goes over the installation too. I'm going to go through this really quickly. I'm going to pause at some of the important stuff, and then I'll go through. But this is all on the slide for reference. So last time we kind of got everything set up on a ROS 2 environment, and today I was going to get a little bit into the navigation. And it's still, the slides I got today is still, we're kind of getting things moving, but it's still like a missing piece of that puzzle. So maybe you want to do something or send you some slides for something else. But we just got the, are you recording?
Could you share that real quick? Like on the actual screen for the Zoom meeting?
Yeah, it should. Is it? Oh, yeah.
Let me make sure
I know, I
gave you
didn't do
permission
that.
to share.
I forgot that last step.
Are you recording this?
Yeah, I am recording this. I just don't know. I assume he can be heard. I hope so.
Yeah, I heard him last time.
Are you seeing it on Zoom now?
Yep, I'm seeing it. Perfect.
So it just basically, this is a basic introduction to ROS 2 here. So it was built for the Windows Linux thing here. We're really focusing on this layer here. You can write everything in, use Python code, you can use C++ code, and then you're expanding this to like MATLAB and Simulink as well in the near future as well. So they try to make a bunch of different, compatible with a bunch of different language, and it all gets kind of really compiled into C. So it's running almost in real time, especially for a real-time OS, and that's why it's really useful for robotics things here. And we're going to write nodes for navigation or control of the goal list of your ground vehicle. Is kind of the goal here. Skipping over a lot of stuff here. This is very useful for in the algorithm development. Everything runs as nodes. It could be a C++ or it could be Python. It has a main method, and they communicate with each other with topics. And so so that particular robot has a LiDAR, which is a scan topic. It has IMU, which is a odometry topic there. And then you can add your own nodes for navigation, obstacle avoidance, pathfinding, and wave. So today we're going to work on waypoint navigation, where you could breadcrumb. Once you have a map of your environment, you could give it just like a GPS kind of thing. You could say, go to this waypoint, go to this waypoint. And you could get through a track just by going through waypoint navigations. But it's going to be subscribing to your odometry and your laser to figure out where it is, localization and mapping. And then you'll be able to, once you have a map of your environment, then you can lay out grid points and then be able to navigate. So everything is published and subscribing to different sensors or algorithms to make something work here. And this is called a computation graph here. And then you can actually see the actual frequency, the control loop of, like this laser scan might be running at 200 hertz, publishing data. Your IMU might be only publishing at 50 hertz. So you can see the rate of the sensor going across the network as well. And what's good about the ROS here, like even though I'm doing everything in simulation, if that was hooked up and we had this shared IP address, I could just, they will automatically auto-discovery, which is in ROS 2, as long as I'm a subnet, I could communicate with that and start listening to topics.
Could you unmute real quick? I just realized you're muted.
Is that something specific to the ROS 2 only?
Yeah, so ROS 2 does auto-discovery, ROS 1 does not. There is a ROS core, so you have like a centralized server somewhere. It could be running on your machine or it could be running on that actual robot. And both computers will hook up to connect to that. So you need to know the IP address of that, and then they can connect to each other. And so, for example, for the ground robot, we'll need to know the IP address of this laptop, or the laptop needs to know the address of that, and then I can make a connection. And with ROS 2, I can have my laptop connected. If that was on, anybody in this room could connect to it and get data from the sensors in real time, and everybody can control of it as well. So that's going to make great for when we actually do, if you want to have someone like manually driving with a joystick, and we went over teleoperation and data recording too, and then someone else kind of looking at the sensor data, you could do that. Everything is just share and broadcast over the network and using TCP, UDP, and you can just, whatever you're interested in, you subscribe to that topic, and then you're able to do an algorithm on top of that. So that is why the advantage of using the ROS2 network, but you could do it on the ROS1 network as well. You just need one more additional information to do that. And so this is an example of object detection using the laser. So here's a laser scan here. It is publishing the message. And you also have, this guy here is actually controlling this. So we actually talked about the velocity command is what makes the actual robot move. This is looking at the XYZ vector, position and orientation, and that command will actually make the robot move in direction. And the end of this lab, or in this workshop had a little bit of that as well. This is doing some 3D object detection, but we're using a laser scan. We can do some obstacle detection. Like if something was in that path, you could try to maybe go around that if you're doing it in your navigation. A lot of these algorithms are already developed. So that's another advantage of using the ROS network. You just really can kind of put deals together and know it's describing inputs and outputs, and you can just kind of drag and drop there and adjust the parameters to make it work for your situation. So you can adjust the laser range to make sure it's working in the same range as yours. And there's really fine-tuning parameters to make it do something. You just need to identify those what you need, what obstacle things there, and then just put them in there and fine-tune the parameters. And you can quickly get something up and running really quick, and then you can kind of add to that. So we worked on getting things set up. So right now, I think people are getting their VMware. VirtualBox is another option, but it is Ubuntu 20.04 for the long-term stable edition. It's Foxy right now. They do have Humble, which is the new latest version that runs on Ubuntu 2022, which is not necessarily compatible with the NVIDIA products yet. So that's the reason why all these nodes are already Ubuntu 20.04 and using Foxy. You can use a higher version or a lower version, and you can utilize Dockers as well to kind of make things talk to each other in different releases. Good recommendation settings here. Use this for your own reference. I have put in some sample code here. This is my editor, so use whatever. And this is how we go through the installation of Foxy. But this is a nice cheat sheet of a list of a lot of commands there. If you're just interested in this, having one all in one place, like this nice cheat sheet in this page here. We went over running programs and launching multiple programs, and that ROS2 run, the ROS2 launch is what you use a lot there. We're also looking at ROS bag if you want to record a data set. I do that a lot too. So once you get your ground vehicle, and I guess you're building a track or something too, maybe?
We're partnered with a lab that has a track.
Okay.
Well, they had a track up until yesterday. They'll have one again.
Okay. But it's in a situation like that, it's always good, even if it's not running, just have the laser scan and move the robot around the track and do a ROS back record, and therefore you could have that data and then you could just play it back and it's like and so you could go back home and actually work on your each replay. So I do that a lot as well.
But you happen to have the same cheat sheet but for ROS1 and other
I
sites?
do. It's actually better cheat sheet for that.
Yeah. You made this by
I would
yourself?
send you just send me an email and I can send you all that.
Okay, thank you. You made this?
This
This
one,
is you.
no, the ROS1 is I downloaded, which is much better than this one here. This one I placed together. So some of this needs to change here, the interface. Some of this got outdated, but ROS1 I've got from it looks a lot better.
Thank you.
Like the ROS Doctor went away, so there's a couple things that needs to be updated. But yeah, bagging is going to be great, and even in ROS1, all of that supports bags too as well. I have some good links on like open source bagging tools that you'll be able to the thing with the bag is you have to start with time 0, and then you have to play it all the way through. Like, so you have to watch the whole movie over and over again. There are some free tools out there that you can just go to certain time. Everything is time sync, so you can say, I could go, especially if yours is hooked up to a server, you can get the correct time, and you can start playing back messages at a certain time again. And so I do a lot of development by just getting a data set, so you don't have to worry about someone taking down the track or whatever. It's always you just kind of playing back that, and you could play the whole navigation algorithm just by playing back the recorded data set. So these are just the basic commands that we went over. If you just do ROS2, or if in the yellow, if you do ROS run, it would just with no arguments, it would give you kind of a list of stuff. So everything kind of tab autocomplete, and so you'll be able to kind of, if you forget the commands, just do ROS2 by itself, and it would just display the rest of the commands there on the screen here. So this is, we're going to use the run, the launch, and we use the, those are the two in the bag is the three most popular things there. And we went through these to just kind of go into an example. We made a own publisher which published this. The name of the node was called Talker. It published 1 hertz and it published a message chatter, and this is a stream message here. So that's a basic example. And then we eventually brought the publisher and the subscriber together, and it was able, the listener listen to that message, and now you have a communication between the talker and the listener. And this could be on, and this actually even be on different networks. So this could be your robot posting your LiDAR data, and I have my laptops listen to that. And in ROS1, you have a little bit extra thing it connects to, but it can still find each other, and you can share information through that. You just need to have the same last subnet. So once you get your IP set up for that, you have I guess a wireless router or something you can all connect into. It might be easier to do that, and you can share messages.
You're talking about like a router?
Yeah, I don't know if you want to just have a like a Wi-Fi router and then everything connect to the NC State network or something. You can get into some issues with the firewalls and stuff. So it depends on how you want to set that up.
I thought we weren't allowed to have routers or.
You can have routers, but they can't be connected to the network or something. There are some regulations with that.
Okay, well the lab has them. I just thought we couldn't have them, but that's
I don't think you could just plug into the wired thing and start broadcasting with that. But you can have your own router, and then all your laptops is connected to that router.
System.
Yeah, and it's disconnected from the work environment. And you can get it connected to the NC State to send a ticket to ECE's help. Dan Green can do that too as well. It doesn't do it for everybody, but it depends on, for a group project, he might do it. So I know a couple of samples already that's using that. But that's the best thing to do is to have a dedicated router that can support the bandwidth too, and that, so you get a nice one that has the Wi-Fi capability to do that. Because the data does get pretty heavy when you start sending, and then we have a bunch of stuff connecting to it at one time. And that will allow you to do a lot of development. You could just have your robot really on the power to maybe on like a benchtop power supply or something, and just leave it for a while, and then you can connect to the sensors and making sure everything gets connected and stuff as well. We went through installing the simulator. So if you don't have a real robot, you use the simulator. You can do the same thing. You can do all your development on the simulator, and that's what we use for the workshops. If we're using the simulator, not necessarily the real thing. A lot of times the hardware runs slower than development than the hardware and the software, so you're always waiting for the hardware team to catch up, and by that time you run out of time. So simulation really helps to get things moving, and then once you get that, it's just transfer things over, so it runs the same thing. You just connect into a different IP address. These are instructions for the simulator. Make sure you go through them step by step. If you miss one, it's not going to work there, and that's what we discovered last time too. They're all from this site here, and this one is from the ROS2 environment, so it does work on the ROS2. They do have a ROS1 compatible one as well. And we just went through the steps of getting that simulator installed. There is some things you need to change here. depending on if you want to simulate does put 2 cars in one. So if you do, I think this is a follow me a part of the competition or something.
There's head-to-head racing.
Head-to-head
Where
racing.
they're against each other.
Okay, so that might be a reason why they have the
You
2
hit
car.
the guy.
So you want to, but this is how you change the number of agents is how many cars are displayed on the simulator. And so this is how you change it from 1 to 2 here. And you can change your start position of your car and the opponent car if you have a 2 there. So they all use this config file, and you can adjust everything doing the config files here.
And I think last time we didn't get past modifying the. Like I think we finished getting it up.
Yep,
Not
and
really
I think
modified.
some people. So I was going to start with getting it up and then moving it around with the keyboard.
Yeah.
I think maybe one person got that far, but
Yeah.
a lot of people did not. So this is also how this raw step is good for if you're missing an installation, it will find it and try to install it. It's not always successful, but at least try. So this is always in doubt, run this command. We have errors, and it may fix this here. And then Qualcomm Build is this main build engine, and so after is this compiler. Pretty much, it's running the CMake compiler. It supports a different number of compilers as well. And we're bringing up, and this is kind of where we kind of left off here. And I'm going to redo these today anyway. To bring up the environment, we need to run this launch command, and it's going to bring up this Python code that actually launches the simulator for the Veracity as well. I did modify some things on that over for this week, but that's kind of how you bring up the environment. And you want to make sure that everything is connected. So this is what it should look like when the environment is fully running. You should have the vehicle itself, 1 to 2 vehicles depending on your simulator. This is your map of the track, and you can create your own track and put it in there as well. We will go into mapping, which you can just you can make your own map and save it. That's the end of this slide today. We'll show you how to create your own map, and then the goal is really for maybe like breadcrumb, some navigation points, and maybe have it try to go through the maze or map or whatever you want to call that. But when you run a command, this needs to come up before you can do anything else. If not, then there's a problem with the installation or something. You need to start over or something. But you have to get this far to get. So that's by running this last command. So if you have everything installed correctly and run this command, this is your final goal. If not, then you probably need to debug something or email or something, and you can try to get that fixed. So once I'm going to go through this stuff today. So this is, I could skip. So yeah, so that's really, in a nutshell, a lot of this is going to be repeated in this slides deck today. So I can go ahead and just switch over to that. Present. So that's a recap. So today, again, I revisit we've already seen this. Agent. Here, I did modify I was trying to get the SLAM, when we're going to SLAM's localization mapping, and I could not get it working with their code, so I did do some modifications with their code. So I changed line 98 and 97, and you'll see why in a second there. I'm going to launch it.
Is the SLAM stuff inbuilt with the simulation, or that's something we'll have to download?
No, that's going to be something you download, but the instructions in a couple more slides.
Okay.
Yep. So I'm going to walk through that process. So I'm going to show you some stuff, and then I'm going to go to the computer and actually do it. So this is what we're going to do when I move over to the laptop. I modify that. When we do that, when I bring up after you modify, you need to compile it again and make sure all your dependencies are there. So I recompiled it, and now I bring up the environment, and this is your goal. It should come up with your simulator. And so we want to look at topics. So again, topics is what you can subscribe to and publish to. And so this is what should be running once you're in the simulator, but these would be the same topics that are running on your hardware. So if I did connected to the robot was on and I was connected to it and I did a ROS topic list, I should see these same topics. And so that's how I can go from my simulator to the real thing by this is connected to a different IP address. But these topics are, some of these, like behavior tree, navigator, we'll talk about that in a little bit here. Click points is what we kind of use for navigation here. Clock, everything has a clock signal, just make sure that we're synchronized. That command velocity is how we make the things move. So when I do the keyboard or joystick teleoperation, it's sending a vector pinging on your keyboard to make the actual thing move. So that's how, if you want to manually drive the robot, you will be publishing to this topic here, or you could publish to this drive topic to. The robot description gives you the actual geometry, the dynamics of the actual robot, so it knows how wide, how tall it is, its weight, and things for simulation. So I can make it go to a goal post, so I can go from point A to point B. I just need to publish to this here, and I can publish this initial pose on the simulator. You won't have that in the real robot. Every thing is color joint where your wheels are, but this map is also going to be the map of the environment, so you won't have that in the simulator. I mean, in the real robot, but we can have that. We bring up our own map server that can provide a map. So the first thing to do, which is to like manually drive your robot around the track, and then a lot of people save that map, and then you can know where your obstacles are. Then you can kind of breadcrumb a course where to follow. So if I don't know the map ahead of time or something, so I'm just gonna give a random. I'm gonna draw a random thing here. Someone told me to navigate from here to B here. So this is B is my goal pose. So everything has a coordinate system, X, Y. We'll talk about that a little bit too there. X is usually we use the north, east, up coordinate system and for ground vehicles. So kind of drew that kind of hard for me to draw. There, X, Y, Z is the coordinate system. So moving forward is always the X direction, and so we always try to move. If you initialize to a compass, that would be your true north, and this would be your east, and this would be up. And this is the convention for ground vehicles, and then northeast down is convention for aerial vehicles, for drones and stuff. And so if let's say this is my home point, let's call it 0, 0, let's just use 2D here. I want to go to this position here. Maybe I want to head it this way and go to here. So I want to go to that pose. That will be my goal. And the goal is for the robot itself to kind of figure out its way through here without doing any, it's doing obstacle detection so we're not running into any walls or edges there. So that is really the goal. And the navigation stack is going to help provide a lot of that thing as well. But it needs to know where these walls are and stuff. So that's where that laser scan is going to do. It's going to be able to go back. It's going to be constantly broadcasting and finding where the objects are, or if something's if something's in the way as well. It's going to see that, and it's going to bring that information back. And that's what we're going to use SLAM. And that's coming up in the slide, a little more details of how that actually going to happen. But you can manually drive your robot through, and that's why the teleoperation really is helpful. And then it's going to build this map, and then we can save this map. And once we save the map, we will have our own map of the environment. And that's what they already provided with you for the simulator. But that's how you build your own map. And we'll walk through those stages in this slides here as well. But this is kind of the steps we're going through here when we go through this slide deck. Just think about this big picture here. And so we need to, so that map is just the drawing of this map here. The odometry is the orientation and position of where the robot is from the starting position. So I started here, I moved the robot forward. Everything is usually in meters, like a meter cube things. So I moved it here to here. It's using the velocity from the IMU, and it's doing the derivative velocity as the position. And then it's getting the position information from the velocity. So it compute the delta P or delta XYZ from the velocity from the velocity information, because that's just double a P dot there. So if you know, and I remember that's just delta, the change in position over delta time. I think it is the velocity of your, but we're looking for position here. So it's doing a conversion, and that would be your odometry. But you can see that has some error in your system.
Are you describing the topic or?
And then odometry in general, and how it does it in the ROS environment.
Okay.
Or in pretty much anything. It's taking the velocity and it's converting to position. And so I'm moving at 1 meter per second, and so I'm looking at the time I move, and I can compute the distance from there. But your clock is not necessarily accurate, so your odometry, what I was going to, is not necessarily spot on. It does have a lot of error in your odometry information. So it's going to be less accurate than using your laser scan. But that is the odometry message. And then your scan is your actual LiDAR. As it's scanned here, it's going to have every XYZ point that comes back, and it's going to be like an RGB of a bunch of points coming back with intensities there. And in this would be your transfer function. We'll talk about that too as well. So that's kind of a little bit of a description of everything that you could listen to or publish to in the ROS environment.
For the ODOM, so it gives you your X and Y velocity, is that right? And then so it gives you your overall velocities. Is there a way to do that easily, or do you just do like the squares?
Yeah, it will give you your SYZ, and it could. So you were talking about you would probably have to do the sum scores of your SYZ to get the true velocity. It's going to actually just give you your X, Y, and Z, and your rotation as well.
Rotation.
Yeah.
Is there a way to get like the way your wheels are turned as well, or like is there a way to compute that easily?
No. So that's one thing you can't get from the odometry. You may be able to get that from these joint states here. Will actually have where all your wheels are, and it's so if we think about the robot, I will show this to you in a second. You have it has 4 wheels. So each one of these has a frame. Also, X is always forward here, and that's Y. And it has a body frame, and then it has a LiDAR or whatever too. So if you want to know that wheels turn like this here, you might be able to tell that from this joint state message, because it will have its XYZ and also its orientation.
Okay.
So you may be able to know how much is that, and then you may be able to calculate the trajectory if that wheel is turning that way as well. I bring that up when I bring the robot live, and we can look at that in the simulator as well. And that's kind of what I was showing here. So I am actually showing all my joints here, and here I'm showing all the joints with the wheels here, and I could be able to look this wheels are straight here, but if it was turning, that one might have a different angle there as well, so I could kind of tell where it's going to go there from that.
Does ROS 1 have a joint state?
Yep, everything. Yep. So that will have a joint state as well. Everything has frames in that, and everything to make things move. It had to have a joint. That's a good question. And so this is a little bit more information about the velocity command here. It's a linear and angular velocity. It's a vector, X, Y, Z, and that's how you can make it go. Listen to that here.
Is that new for ROS 2?
No, that's the same. All of these are the same in ROS 1 and ROS 2 here. They changed the name a little bit. It's actually ROS message. ROS 2, they just slightly changed everything. So it's easy to go back into, when you get into coding of this, you have to import this header to actually use the message. And so, is that too low on the screen? Can you see that?
I don't think it's gonna see anything on there. It's just seeing what's up there.
Okay.
Yeah, the whiteboard is a goner in terms of.
Okay. It's not that big of a deal, but
Oh
so
wait,
this
wait,
could-
wait, wait, I understand what you're saying. I was being.
Yep.
Yep, it's good.
So this is how you would import that. This is, I'm going to use C++, for example. Include. And then the ROS one, it doesn't have this extra here. So that's the only difference. And they added this extra tag here. It's plural with S. But, so they try not to, once they get something extended, they try not to mess with it that much because you generally have a different version to different messages.
Yeah.
And it gets a nightmare. So we'll bring it up, we'll be able to run it with the keyboard, or you can do this joystick, and it's just going to go from twist keyboard to joystick. And that's how you'll be able to move it in simulator, and that's how you'll be able to move it the real thing as well with the same, but it's posting that velocity message. And so here, when I ran it, I actually come to listen to that topic, and you can see that I moved the robot backwards. So that is, remember X is forward, so if I want to go backwards, I'm just going to go back to a negative 0.5. And it's going to actually start moving back at that particular velocity. And if I want to stop it, I just want to publish 0, 0, 0, that's stop. If I want to go forward, I just need a positive X. If I want to go to the east, I just need a positive Y. If I want to go to the west, I need a negative Y. And since it's fixed to the ground, the Z is not going to do anything for a drone that would go high, go up or down. Yep. And it also has a drop command. That's another way to using it as well. And I don't really use that as well. And then, yep.
I just had a question about the joints. Just like, so when you create like this ROS2 environment, do you create like a 3D model that you tell it has these joints when you import into ROS, like it knows like
yes,
how many
it
turns
does
it's
have, and I can show you exactly where that is. Every, in this description node, and remind me if that, again, when I come up, it will have it, and I will show you that in a second, man, exactly how that's described in there. So you have to give it a, when you create your new robot from scratch, you do have to give it a URDF file, which is the description, universal robotic description file of how you word the XYZ, and you can also put in your weights and masses too, and for physics engines and kind of compute a lot of stuff in there as well. Those are really good questions that I didn't think about showing that, and that's a good idea. That is, I do that in the Masters 400, Masters Revised Plus.
Our system uses acronym.
Why is
is that different?
And that's why I was curious with the command velocity or whatever it's called, because I have not used that before.
so? And that's what the joystick thing is, just publishing the command. And as usual, my laptop wants to do something. I'm just going to quickly power that off. It's just camera shy. But the thing about the VMware is pretty quick to look up. So we'll walk through, bring them back up, and I kind of dive a little bit more into that. I will show you what those description files are and stuff on the actual simulator, and then we'll talk about. I'm going to skip over building your own program, and I want to talk about navigation, and then depending on time, we'll go back to building your own program. It's almost back up. All right, so this is my So right now we've been putting everything in the sim workspace here. And I'm going to try to answer some of the questions you just asked. So we built this package here. Oh, we downloaded this package, and it had this kind of give you an idea of what you can run this in Docker. So they did a Docker version equivalent of that, which I do like to utilize Dockers a lot, and especially for different environments. But we're running this locally on the machine, not in a Docker container right now. It has a bunch of folders. These are all optional here. This is a Python class that I don't see a source. If it was a C++, it would be a source directory where you would code there. So that it has, this is the location of the map, and we can, I think we're using this map here now, but you can see we can create our own PNG map. We have this map here is available too as well, and that's not a map. We have these two maps available, and you can see we could draw these out and we can make a equivalent YAML files for that. You just need to give it the name of the and then your origin here, and pretty much you have it. So you can use a vector program, Adobe Illustrator or something, make your own map, save as a PNG file, and bring it into your map folder. And in the config file here, you select the name to the map there without the stitching, and then it will show up in your simulator. So that is a good thing here. Here's the config file that we talked about earlier. Is the topics, again, the scan is your LiDAR, your odometry is going to be a velocity position estimator there. It does have two cars, so one is the ego is your car, and then the opponent is starts with OPP. And I can go to 2 here, and then I can give my starting point of the positions of that. So that's the config file. Inside this file here is the gibberish. So I changed this line here. I wanted to change the odometry, and I'll show you why in a second. For the SLAM doesn't like the way it was doing it, so I modified that Python code there. We'll revisit that in a second. So this is in the launch folder. When we bring it up, we're doing a ROS launch, and this is what we're actually calling. So it's actually going to run a bunch of other programs in the background. So one of the things it's bringing up is the robot publisher, which is publishing information about the robot. So you asked about the geometry file. So that's what this Zacro file is here. It's just how it needs to be there to describe what the robot, so it knows the size. Even if you know a SLAM, it needs to know how large that robot is. And so this robot has a width, and this is in meters, so it's probably the same as that guy here. It's 0.332. It's a wheelbase, the width, and the height here. And this is all your information about the actual robots here. These are like variables, and they use into this file here. So this is a universal format for describing. So you could have, they just made it black and blue. You could change the color, it doesn't really matter. But you can put material properties in there. They didn't add a lot to, but you can put masses in here if you're trying to do some more simulation there. If you want to go into a curve, whenever you want to do momentum to figure out something. So you can add a lot more into this, but right now they're just using color. So it depends on how advanced you want to get with that. But you're describing the base length is the base. I'm going to bring up the gazebo to see the actual frames for that. But these are the frames. This is where the LiDAR is located. It's XYZ position from the origin. And so you gave you the, so if you move your LiDAR to a different position, you might want to just figure out the new height and stuff, and then put it in here.
Where do you set the origin on the car?
The origin is always going to be the base, and it's always, you can't set the origin, so you set everything relative to the origin. So that origin is always going to be the 0, 0 position there, and then but that's usually the centroid of the vehicle.
The center.
Yep. And then you can measure, okay, get a real say that LiDAR is regulate it. And what I do, I bring it back up and then I make sure that it looks sense, I think, in RViz. So that will make more sense in the second, how to really figure out where the origin is. And but make sure that this matches, if you want to make sure the simulator matches the real vehicle, then just go double check these numbers and make sure they are correct here. I know if you mount it in a different spot than the actual simulator, you can change that here. But this is where the left wheel hinge is, right wheel hinge. And so these are the things you can look at to see if that wheel is turning to the left or the right or whatever when we subscribe to this information. And so I think that answers something what you were asking before. So now I'm just going to bring up it's always good to source your install directory, setup, bash, and I'm going to, this time I want to launch that program here. So the package again is called the directory. The package is this name here, and I actually want to launch, but I want to run this program. So you do ROS2, and in doubt you can do ROS2 with nothing, and it's going to give you a list, kind of help you out. But in the ROS2 launch, the name of the package, which is the intent, I can auto-complete with using the tab button. And I could, if I don't know, I could just double-click tab, and it sees this Python file here, the GenBridge. And I'm going to start, and I'm going to hit tab here. So it's going to bring up this Python code here, which just brings up the whole RViz Gazebo environment. And again, it needs to have, it takes a little bit, there's some errors here, and then eventually it comes in with the LiDAR data, and that's how you know it's working. But here is my car. I didn't put in, you can actually put in STL models, make it look like a real car. I just use in here, I just use boxes here, it looks like. But you can make this look more fancy if you really want to for a simulation. A lot of times they don't really go into details. So here, this is my car, but I can actually make it look better than that. So a couple of things here. It was asking about the frames of the robot. So I'm going to go to the robot model, and I'm going to spend this link here. Let's see here, enable. I'm going to add another thing. Add by hitting the add button, and I'm going to add this TF, transfer functions. And now I see all my frames here. And
What are
so-
you adding there for the green lines?
Yep, so I can delete it, this here. So I went here, I wanted to see we was asking a question about the frames earlier. How you know where the center is and how you know where your wheels are, just to verify that your model is correct. I'm gonna do, it's not on here by default, but I'm gonna go hit the add button. And I'm gonna look for TF, it's my transfer function, it's gonna transmit my frames assignment, this guy here, and so to my simulator. And once you do that, I can see the actual frames for my hair robot, and then I could show names. It's going to get a little clustered here, but I'm disable that, and I just want to know where the center of that. The base link is what is considered the center of this robot. It's 0, position. So it's actually described as the very back center is where the 0, position is there of the robot. So if you totally go to the 0, point, it's going to go to the back of the line right there. It looks like. And then if you want to know where the left wheel is, let's just do the front left to give it a little bit of space here. So if I turn that wheel, I can't do it in the simulator, but if I had it the real thing, if I moved it down, that frame would probably turn to as well. So if you want to know the heading of that here. So that's my left wheel, and here's my right wheel here. And so that's provided in this file here, and it is going to, and when you move, it gets updated in real time. So that's the beauty about the simulation environment and the real environment. The ROS environment is going to update those transform matrix as you move the robot through.
I have the robot model, but I don't have
Don't-
frames or I don't have TF.
Yeah, it's not there by default. Do the add button, and then it should show up here, and then you need to scroll down to TF.
Is it by?
It should be towards the very bottom, actually.
Okay, let's check it. I have acquired it. Yay!
You have it? Cool.
Mhm.
And
So
then,
what are those? Oh, sorry.
Yep.
If you enable everything, like going from the wheels, there's like purple or pink arrows. Are those? I get that they're going back to the center, but like, what exactly are those?
which,
I just.
enable everything,
Yeah.
and
You see, if you go back to the center, there's like pink arrows going back to the zero origin point.
I don't see it here, but I wanted to demonstrate that. Because I'm at the origin. Another thing I'm going to do, I'm going to actually move this. I'm glad you brought it up, because that's where we're going to go next. So this 2D pose estimate, I could change the initial starting position. So I'm going to click here, and then I'm just going to click here and move it. So I think you're talking about this area here.
Oh,
Maybe not.
I was more talking about these right here.
Oh, I never zoomed in that close.
You're overanalyzing this, Chris. I don't want you to look that deeply at
I just be showing the origin of that. I never
It's
really.
spikes to keep its
Yeah.
enemies off its tail.
And then I also remember in robotics here, we use XYZ, but it's also RGB. So in doubt, just remember red, green, blue is the order, and red is always X, G is always, green is always Y, and then blue is always Z. Yeah. And so, and that's always the robotic standard, RGB, red, green, blue. And so when you draw your axis, like in class, I usually actually use like a color thing. So it's easier if you get into the habit early to draw your X's out in the right colors, and then you can kind of know things by just looking at visually where your X is, the direction. So it's going to be headed. So if I give it a vector X 0.5, you can see it's going to head forward straight ahead because my X direction is straight ahead. And I did the 2D pose, and then I just clicked on something, and I'm moving the robot around. And you can see how the LiDAR scan is kind of changing too. But my map, this is my origin of the map here. So this is my 0, point of the map. And right now it started at 0, so you didn't see it, but I could move this guy here around. And I could build a map this way too if I wanted to. Because you see my LiDAR is updating as I move the robot through the kind of maze here. So I just turn the directions too. So now you can see so this is pose estimation. So I can also hold it. I can give the orientation and the position. So pose is position and orientation together. So that's how you could, and that's how we could drive. Eventually, that's how we could initially drive the robot around too, by just going through and a navigation exercise. And we're just gonna give it, and the waypoint we're just actually going to give it breadcrumbs, kind of like this. Go to here, and then go to here, and then we're going to keep going till we get it all the way around, around the track or whatever. So that is the basics of the RViz and answering some of your questions with the frame there. So once we have it up, instead of moving it with that, let's move it around with a keyboard or mouse. And so once you get your robot up, once you get connected to the same thing over Wi-Fi, someone could go in the computer and just run the ROS2. We're going to just run this command now, the telo-op twist matrix, and I'm going to use my keyboard. If I had a joystick, USB compatible with Linux, you can use that as well. And I'm able to drive it with my forward is I button, K will be. So I'm going to give it an I, and you can see it's actually moving forward. I'm going to stop it, and then I'm going to go back to J. So I just did a quick thing when I did that. I'm gonna open a new terminal just to show you something. You're gonna go to that directory, sim underscore workspace. I'm gonna source this install directory, and I want to look at the topics. So I'm gonna do ROS2 topics list, and I want to ROS2 topic echo the. I don't see the topic I was looking for. Let's again.
Mine are very
Mine's going very slow. What is holonomic registration?
There we go. Now we got everything.
So I'll give you one.
Echo this command velocity topic.
It shouldn't take too long. Yeah.
And so now I gave it a command 0.5. I hit the I button, and you can see I was giving it a linear velocity only. So it's actually giving the force of that in the X direction at 0.05, and that's what's making the robot go in the X direction. And then I made it stop. I hit a K button, and I gave it. It just told it to put a 0 onto that frame, and that's why it stops. So I am the command velocity when we're publishing a topic. I can make a robot move by just giving it velocity commands, and I can navigate that way too. So that sample code I gave you on the first here actually goes into writing your own code to make it go forward and backwards. So here we're not going to go through it just to take of time here, but if you write this program here, not on the PC here. Here is a Python code that I wrote to publish that twist message, which is that velocity command. So I published it. So this is making it go. This is going to make it go forward and backwards here. This guy, this message. What is my X, Y, Z?
It's gonna go
Just
forward,
going
right?
forward a little bit.
It's going to go forward, and then if I want to go forward faster, then I'm going to ask it to be higher.
So did you just make multiple functions that do something, or?
Yeah, so that's what I was going to have you do for the last time I was here. Make it, this one went forward here, and then in 10 seconds, it stopped. And so it's just, so I wrote a Python code to make it go forward and then stop. And then, so I'm providing that here too. And that's just going to make, that's one way of navigating, but we could go much easier. We're using a navigation 2 class to do waypoints, yeah, but this is like a manual way of making it, or you still writing program to make it move here.
Yeah.
But we have a lot of built-in stuff to do it better. But this is just a manual, because you will have to do a lot more work in this guy. But it's possible.
What's the create timer?
Yep, so everything is going, this is a timer is going to get interrupted. It's going to call this function at every time your time period happens. And so we do that a lot in a lot of robotics here does that. For example, in this talker class, I wanted to publish something every 1 hertz. So in this code here, every 1 second, this function gets called, and it's going to do whatever inside that function. So this is a loop. All the ROS code is running in some kind of loop, and the loop is running at that 1 hertz. And so we use timers a lot to make something happen over and over again. And then that timer is always going to get called back again. And it's pretty accurate about, if you say 250 hertz, it pretty much hits that 250 hertz there. So I wouldn't go too crazy with speed, but it can handle pretty high speeds too as well. So that's how I do a lot of control systems. If I want it happening at a certain frequency, I use a timer, and it's guaranteed to almost hit that at the right thing here. But good question. So that is the basics. So feel free to run that, write this code, and roll through these slides. and let me know how it works here. But I'm gonna give you a little bit better way of doing it as well. And that's using SLAM. So center making an algorithm to make this thing move. We're just going to, that's the beauty about ROS is a lot of this stuff is already been done. You just get it in 90, it's just do some parameters. So it's build for, I guess we're going to probably do more of a ground-based thing here, but this is what we're always going to like. This is a lot of room here. It's going to have obstacles in the way, but we need to, like if I'm going to drive to, let's say I'm driving to Wilmington, back in the day, before GPSs came out, you go get a map and say, okay, I need to go down 40 and go. So I need to make a map of my environment, and then I need to know where I'm at in the map. I'm in Raleigh, and then I want to go to Wilmington, so I need to know my starting point and I need to know my destination point. So that's all we're going to do in Robotics 2. We're going to either download a map or make our own map. And then we need to know where we are on the map, and then we need to know where we need to go on the map. And that's the information you need to do for navigation. And it can be done in space, underwater. You can't use LiDAR underwater, but you can use some other kind of system. So you can use a sonar or acoustic sensors. Doing the same thing, you need some kind of laser scan or some kind of rangefinder, that's VIZ, and you need your IMU. That's only two sensors you really need. You need to know the velocity to get your position back. And you could use this algorithm. So, and those two sensors available in MSP, underwater, ground, and even in the in space. We have those sensors. We have sensors equivalent to that there. And so it's called SLAM. We're going to do localization and mapping. So localization is figuring out where you are in the environment, and mapping is making a map. We're going to do those at the same time, and that's why it's called SLAM. But you could do those independently. You could do mapping first and then localization. And that's called offline, but we're going to do everything at the same time, so we're going to use online SLAM algorithm to do that. And so it has the two stages. We have to do mapping first, and then we have to do localization. But like earlier, we need to build a map. We need to know where our position is. And but it's like we're taking out which one you do first. It doesn't really matter which one you do first because it's really going to happen almost at the same time here. So we need to estimate, we need something to know where we are. So we're going to look for landmarks. Even if you're doing regular navigation in your car, you look for a Wendy's or a stop sign or something, turn left, turn right there or something. We need landmarks that are fixed in your system. So in this case, you have probably a track that has fixed walls or something like that. And you'll be able to use those landmarks to kind of figure out where you are in your map there. But that is required. So you can't have a moving track. It needs to be, or in real life, in navigation, that environment is going to be static in a way. So you may have stuff come into the environment that's moving, but most of it's going to be static. That road is not going to change in real time. It's going to be a road that's pretty much there for a while. And we need to estimate our position on that, and we're going to kind of go through this in more detail in a little bit second here. And so we're going to use the laser scan. We can subscribe to that topic, and we're going to use the IMU, the odometry information. Again, that's the estimated position of the based on velocity information of the IMU. It depends on the quality of the IMU, how well it does that estimation. And we can use the algorithm called extended common filter to kind of give a better estimation of where you actually really are in your system here. There's a lot of error and noise in these systems, and the common filter is going to kick out that noise to make it a better estimate of your true position in space. So this is a really try to draw a picture of how this thing works without going into a lot of detail here. But this is the algorithm here. I'm going to do this extended common filter, the odometry information, and I'm going to observe where I'm at, and I'm going to look at landmarks. But I'm going to describe it as this picture here. If you understand this picture here, you can understand the basic SLAM and how it works here. So here's my robot. Here's triangle. These are landmarks, walls, whatever you want to, whatever the LiDAR reflects back to your system. And these light bulbs are the LiDAR beams there. So robot sees the three landmarks, and it knows its XYZ position of each one of those positions of that. And so I could triangulate my position back here. So if you know two things, you get your XY thing. If you know three things, you get your XYZ position by So I know my distance from you to here and then here to here. I can triangulate my position back from there, knowing this 3. And then the more you know, the more information. That's what That's how GPS works as well. It goes to it looks at the satellite, looks at the time to the satellite, and then it calculates its SY position, longitude, latitude, altitude from that. So I'm going to move the robot now in any random direction. So I move the robot a delta position forward. And so I was here, and now I'm here. I can use my odometry, said I move 1 meter forward in that direction by looking at that sensor data. So I've got that here, and now I'm going to turn on my LiDAR, and I'm also going to get my position updates from my LiDAR scan. So it sees the 3 objects again, and it computes its position again. So I have 2 different position information. One I computed from my LiDAR, and one I computed from my odometry information. And they may not match. I may have a really high quality LiDAR system and a low quality IMU. I may have a high quality IMU and a low quality odometry. So in real life, my LiDAR may think I'm here, and my odometry may think I'm here. So where am I actually at in this situation? You really don't know. You could be here or here. More likely that your LiDAR should be more accurate. This has a really high resolution. It can have noise, and then it kind of gives you a bad thing. The odometry, again, is an estimation. And so that's what the extended common filter is going to do. It's going to filter out that and figure out your estimated position. So I'm going to take both solutions, and I'm going to kind of and do an estimate of where I really think I'm at. So the red is where I think I'm at, and that's what SLAM is. It's going to, all you do is doing a random movement, and I'm looking at 2 sensor data, the odometry, and I'm looking at my laser scan. I'm going to compute my position and my orientation from those 2 data, and I'm going to use a extended common filter, and I'm going to estimate my actual real position. And that real position is an estimate of where I think I'm at on the track, or where I'm at in the room. So I think I'm at this XYZ location on the track of the thing. And that's pretty much it. That is SLAM in a very simplified manner. But these algorithms are already going to be able to do that for you here. And what we're going to do, there's grid-based SLAM, which I'm going to take my map here and divide it into grids now. So I'm not using the points here. And I could make these grids larger or smaller. So we're going to use, that's be one of the parameters you need to adjust when you make the algorithm run better, it's slower. So everybody's probably going to use the SLAM, but fine-tuning that grid to what size is going to make it react. So I could have a grid like this, or it could be huge, or it could be really tiny here. And those are the things about making the algorithm run better or not. And it's going to find that whole object, and it's going to try to get a position for that whole thing here. And that's what that'd be one of the parameters you use in when you're tuning your system here. Because it doesn't know what environment it is. It doesn't know what size it is. So that is grid, and you also have landmark, which is a single point here. The algorithm that's in ROS is a grid map algorithm that's built, and it's going to give you a map like this here. And let's see here. So yeah, so just make sure that it's in a stationary environment when you do your first mapping, and which is you should have. So once we have a map of our environment, we're going to create obstacles from that map, and that's what the grid is going to matter then. If I want to go from here to here, it needs to generate a path. If that grid was really large, it has to generate a path like this to get to there, because it's going to avoid. It's going to say that this grid is occupied. This is occupied, and I need to compute a path through that is here. If I'm going to here, and I'm using a small grid size, then I have plenty of room for that robot to kind of move around to get to there. So I can make it tighter or thinking by changing the grid size. And that's going to be, these scenarios going to be a penalty, what we call a cost map here. So when we're doing obstacle or we get penalty if we go into this area here, and so it's gonna try to avoid that area. It's no penalty. Penalty is 0 here. Let's just say it was an 8-bit of a 4-bit there, 255 here, and it's gonna try to go through a path with the least resistance, just like current, and compute its own trajectory path, and that's where we can build a cost map to. So each one of these cells is going to have a cost associated with it, and it's going to compute a path using the less cost to that destination. And that's going to produce a trajectory profile, a breadcrumb from point A to point B, and then we're just going to give the motors a velocity command, and we're going to try to navigate through that. So those are the steps of timing navigation that's already built into that. Another thing that's built into the NAP2, we have a static map ahead of time, but it's always updating. So as I go along and I drop something in here, it's going to compute that, put a grid, and then give a cost estimation to 255 there. And again, it wants to go to the least resistant. It's going to route around that. So it's doing live updates as it goes as well. And so that's the beauty of using the NAP2 stack or even the NAP1 stack versus writing your own program, giving it velocities here. And that's what we're going to utilize in this class or this workshop. So to do that, and this is where I'm still working on these slots here. Didn't quite get them ready. This is the NAP2 website here, and this is behavior trees. We're going to talk about that later. But the transfer functions, here's that map that we created, and this is the sensor data. Again, this needs odometry and this needs laser scan, and it could do all this on its own. You just going to adjust parameters like the size of this to make it run better or smoother or whatever, or your filtering algorithm. You're just turning knobs to get a better, faster track time. Yeah. To get the things set up, you need to install these packages as well, the SLAM2box. So we'll run through that, and you need to install these navigation, and that's really it. And we're just going to run it. So when I go back to the laptop, we're going to talk about how you can configure that using these parameter files, and how you make your map. And we'll talk about saving your own map, and then we're talking about running a navigation stack. And I'm just going to show you those things, and then I'll let you go. So I'm going to switch back to this here. And there's still more to do on that. These things don't quite work yet. I haven't run out a little bit of time. But I'm going to show you what I have so far. Let's see here. Where is that? So, ArcGIS, we're still got up and running, which is great. And we have the Tello operation running. So in this case, you can see we already have a map of environment, so we don't really have to create our own map as provided. But if we didn't have a map, like if we put a robot on the floor, all we do is take that and we'll just drive it around using the keyboard or whatever, and as it goes, it's going to create its own, it's going to create the black lines. In this case, it's not making new lines because it already knows everything. And that's how you will have a map here. But we want to save it for use. So in the panels, add new panel. And after we install that SLAM2box, we're able to run the SLAM plugin. And now we have the ability to save our map and utilize that. So I'm just going to call it my map. And my map here. Hit the save button. It takes a little bit. So this is an unknown environment. You put your robot down, you drive it around with the laser running, with the SLAM toolbox running, and then it will appear on your screen here. And then I just open this toolbox and I hit save. Now I have my own map of the environment, and it's going to save in your root directory here.
You're not getting that.
I don't see it. And now you're able to utilize that map into your algorithm. Did you get?
I don't think we're getting this on the video. I think we're just getting that one.
Ah, yeah.
Oh well.
On the recording I have both, because I'm recording through the lecture software. Is anybody on Zoom?
I'm on Zoom. Like I'm recording.
Yeah.
Okay, as long as you.
Yeah, so I'll send you the video link to this, and then we'll have both.
Okay.
Yep.
Awesome.
Because it's both are connected down to that server. Yeah.
Perfect. Thank you.
Yeah, I forgot that. Let me switch it over to. But, so that's how you save a map that you already don't have, and so that's really so. Again, first step is going your map. So really, you don't have to do much work there. You just need to subscribe to those two messages, the odometry, and then run. This is how you install that, the software for it. And then we need to run this command here. And we just need to drive the robot around. And then we just hit the save button. And now we have a map we can use to actually start putting some breadcrumbs and start to do navigating. And so if I've watched a bunch of videos of my teams in the past, that's what they did. They did like a test lab. They just drove it around and they saved it. And then they just started, yep.
Now, how fast is like SLAM? Like, would it work for racing, or would you recommend something else?
No, I would recommend driving around slowly for the first time and saving that, and then loading that map back in, and then do waypoints for the fast and for racing. I wouldn't do it. I wouldn't do it in real time. I would run a pre-loaded map. Yeah, it could. The reason why I say that is going back to here, since this is. And that's the simulators are great, but they also have a problem. Is like you can see here, these laser scans almost perfectly in this picture here. But on the real, it's not going to be that. It's going to get false stuff all the way in here, and then especially with moving it, faster you move it, the more you'll get some bad results in there. Yeah. But in the simulation, I can run this at real speed. I could run it at the same time and wouldn't have any problems with that. But you want to have a lot more noise. So so once you have your map, so that's the first thing I did is I made my map using the first command. And then I'm going to change some parameters here. I saved it to my computer. And I'm going to use this preloaded, to answer your question later, I'm going to use these preloaded maps in the race time, when it's time to race, and then it's still going to update as it goes, but I don't necessarily need to worry about it because I have some preloaded information. So I'm still kind of following this algorithm here. I build a static map, and then as we race, I still want to use some real-time LiDAR just in case something changes in the map. Something got in the way or something like that, it would still behave behind that. And so this is the static map by running this command line here and saving it. And my static map is named robotmaze.safe. So that will make sense later when you actually get the robot moving in and start doing that. And we run through this PowerPoint slides on the real robot. So that's the save map. And then I need to tell it where the map is. So I need to edit this file here, map parameters, and I saved it to my location here, and that's what it needs to know to when it runs in real time. So you just need to give it a destination where you put the map you saved it to. And then need to rerun it again, and now it's going to be running in real time. So I want to demonstrate that probably at another time when I got one bug I got to fix through there, and then maybe have more stuff to run into, then that might make more sense there. But that's where I skipped over this set of code here. I was going to have you do this here. It's pretty much making going through these steps of making your own program, and that just gives you practices to go ahead and like writing your Python code here and executing. So if you write this program here, this is also it's utilizing publish and subscriber. So you actually writing that velocity command, and it should go forward, and then it should stop. So you can go ahead and you can try that too as well. Yep.
I had a question related to this, but I was kind of wondering, like, so when you give it that command velocity, how does it know to transmit that to the joints and like to the wheels and stuff? Like, if I had a different robot that didn't have wheels but had like tracks or something, how would it know to like give it that?
And that is why we didn't really do a good job here. But in realistic, when I do this here, a mature property, I will actually put in mass in there. So it's giving, so if we adjust that mass with that velocity, it's not going to move. If I give it a 0.5 x direction, it's not going to move as much there. And so it doesn't have, so this is similarly in an ideal environment. So it's going to, they could behave a little bit different in the simulation versus your reality because you don't have that information. The more you describe the information, the more likely it's going to happen. It is running a physics engine as well inside of that.
But like in terms of like turning, like if I give it like both an X and a Y, like this car knows to turn to go that way.
Oh, okay,
like,
yep.
How if you had a different robot?
Okay, yeah, so that is more in the actual controller code, the
So that's the controller dot.
yeah, it's not in these slide decks at all. But if we go to, so there's a slightly different software that's running in the simulator than the actual. And what I showed you is kind of a reduced set of that, but the actual one you load under there has the differential drive controller software that is computing, taking that vector and say, okay, motor 1 has a PWM signal of this, and motor 2 is. So it's taking that velocity and actually you tuning that PID to actually make that velocity respond to like it should have there.
Okay,
So that's more of the hardware side of the thing. But right, so software just takes that velocity and say, okay, move that. But the actual controller taking that velocity and converting it into PW motor signals to give that velocity direction. And then you want to verify that vector does the same vector, and you want to do a tuning of those parameters to make sure if I give it a 45 degrees, it actually went to 45 degrees or something like that.
Okay.
Yeah.
So that's something that like comes predefined, but if you were to change it, you have to change that code or
Yeah, so I think I saw it earlier. I'm gonna dig. Let's see here, in their website. I was reading through that earlier. Building the car. So using this speed controller here, which there was some code. Let me go to their, I can't remember their big bucket. It's, in this format. Let's go to their code base. That's not it. You know where their
Where their code's at?
yeah, the
there's
Bitbucket
a-
site. Here we
there's a
go.
stack, right? Yeah. That
This
might be
is
their
what I was looking
build
for.
documentation.
Their
I do think
GitHub.
their code's for ROS 1.
So this here is their repo. I think it's right here on the system. Yeah, this is it here. And so this has the branch for Foxy. And so this is the actual so this would be what you would load onto the real vehicle, and it's going to have the same. Once you get it running, it will have the same topics that publisher that you have on the simulator. So this is a drive stack here. Haven't looked at this in detail, but so it does have its teleop thing here. I'm looking for a geometry file here. This dollar interpolator might be it. Yeah. Yeah, so it's calculating the steering angle, and then it's going to actually, I think it's publishing these RPM into, I know, so this is the way it's going to be, so you have some parameters here, like the servo, yeah, so it's publishing that to the servo. So it's going to figure out from the angle is going to say probably different servo values, something like that.
Okay.
And you need to, I was looking for, delta servo, some more math, like computing. Sometimes there would be more stuff than that. Let me look at the older code. Yeah, we could talk a little bit more about the hardware stuff too. I had to find exactly what it is, but it looks like it's taking that in, converting that vector into some PWM commands.
My other question was, does the car have like memory? Like, does it know, like, oh, I just went around a corner or something like that? Or can you only have like real time?
Well, you can retain it, but you have to do that, right?
Yeah, so it doesn't necessarily know like past history. It knows where it is now, and it knows its goal. So yeah, if you wanted to know you just went around a corner, you would have to you would probably have to data log your previous point before you move to another or something like that.
And you could just do that with like regular like logging like a text file or something, like you just keep the data in, or is there other ways?
Yeah, so one thing I would be doing would be the back file, but you want to know if you want to curve for algorithm purposes to do something differently. You will probably have to write your own node that listens to, go back to here. So as I move, I'm going to move the robot. So instead of subscribing to the actual, let's look at some other topics. And what is that, a DOM I was talking about earlier? Let's just echo that. And I'm going to stop it because it's probably hard to see. So this is its linear acceleration. It's not moving, and angular acceleration, so it's not giving much information there. But this is its pose, its position, and orientation of the vehicle. I'm going to move it a little bit forward for a couple seconds. And I'm going to keep going a little bit more. I'm going to stop it. So I went from here. Let's see if it's this new window. Let's compare it side by side. Let's see here. Raw's topic. I go a DOM. I may have. Okay, stop it. So I was going negative X, so I went backwards here. So if I subscribe to this pose message, I can get its position out. Where is that? So here's your robot. And again, it's broadcasting its ODOM information. But ODOM.pose will be its X, Y, Z, and then its roll pitch and yaw pretty much out of there. So if I wrote my own node here, subscribe to that, I could just keep that information and retain it there too. So I have some kind of loop like we were talking about earlier at 10 hertz or whatever, and I could maybe make a vector of poses and append it to that vector every time I got it, and then maybe look at delta poses and kind of see if it's doing something differently, or figure out how it went around the left corner or something, and by the way where it changes in orientation or something. Did a little bit of logic there.
Okay, that makes sense. What is that? So the position X, Y, Z, I get what that is. What's the
orientation? It is a vector, but it's a quaternion, not an actual. It's representing row pitch and yaw as it's easier to do that in mathematics and as a quaternion. It was going to have an X component, a Y component, a Z component, and a weight component as is a vector. And there's another way of saying row pitch and yaw. It's a very long explanation to that, and you probably heard of gimbal lock and stuff. And representing as quaternion, you don't get gimbal lock. I could send you a paper on that, but that was a very bad answer to that. But you could probably just do Google quaternion to row pitch and yaw, and then we give you the equivalent row pitch and yaw back. Yeah, your rotation X, rotation Y, Z. But yeah, the problem is a rotation matrix. If I rotate 90 degrees, and then do another rotation 90 degrees, it's kind of harder for you. But you would never get into here because you're rotating by a 4-degree freedom vector. And I did a lecture on this in one class one day, and no one got it, so I stopped explaining it. But there's a good YouTube video too on it, and it probably puts you to sleep.
Okay.
But utilizing it, you could go from, there's a couple ways to do a rotation matrix. You could do rotation matrix, and this is also 455, 555. It's a 4x4 vector, and 3x3, so this is R11, R12, R13, R21, R22, and this is why GPUs are so good, because it does matrix math really good. And this is 0, 0, 0, 1, and this is X, Y, and Z. So this is my rotation component, and this is my translation component here, and I can represent that as a 4x4 vector. And GPUs like 4x4 vectors, so I can make this. If I want to rotate, if I want to go from here, and this is where we're at. We want to go from A, and we want to go, let's go to this place here, D. And I'm going to give you a little bit of, say this is 2 meters, and this is 2 meters here. How do I go from point A to point B?
Well, the best way to just be to translate it directly.
So you need to translate in X direction. 2 meters. That will put you here. And then we need to translate in the Y direction. Yeah, translate in Y. 2 meters. That will put us here. But this is, and then I need to rotate
in the flip.
Into the Z. Yeah. And so this is. It's a 4x4 matrix, multiplied by a 4x4 matrix, multiplied by a 4x4 matrix, and that's going to be equivalent to a 4x4 matrix. I could do this in the CPU, but I could do this in the GPU really fast. And now I know where my orientation and thing is. And I can extract my row pitch and yaw out of that, or my quaternion vector in this case, and I could extract my X, Y, Z position out of that. And then I could, that's called a transformation. So that's how you go from one point to the other there. And we do that a lot in robotics. But we represent it as a Q and XYZ. And the 4x4 matrix is too much information to do over the computer stream, so we never do a matrix here. So there's always a Q value.
Okay.
Yeah. And then if you do rotation, you don't really know if it's in degrees or radians, and this is unitless, which as well. And so that's another reason why we use quaternions as well.
It's unitless?
Yeah, so it has to have a sum square error of 1, but it's these are not radians or degrees. It get converted back into radians to degrees during the conversion.
Okay.
So you don't have to worry about that as well. But the beauty of a quaternion is, so again, and it's usually called Q or Q dot. In MATLAB is a vector like this, is X, Y, and Z. This has to be, if you do the sum square of W squared plus X squared plus Y squared plus Z squared, it has to be equal to 1. That is the condition. So a 1, 0, 0, 0 is just a regular origin. Again, that origin is X here, Y, right-hand rule. If I want to rotate by Y, you just put a 1 there, and 0, 0, 0, and then that's a rotation of Y and things there. And you could do Q dot, this is a dot product of the two vectors, and to do a rotation now. If you're interested at 435, you take the course.
Okay.
Yeah.
I'll take the course.
Yeah.
Thank you.
But that's how, in a way, that's your position and orientation of your robot. And remember, that's going to be at the base link. So the back of you have to figure out where that's at. So that's going to be the base link of your robot. And so that's not taking account of look at your bases again. It's at the back of the vehicle. So you have to take account of the size of your geometry too as well. Any other questions? All right. I'll upload that to the site. And that will get everything fully running. You can do and send those stuff to you as well, like a full command suite. The next thing to do from there is, once we get this far, we can do waypoints pretty simple by navigation plugin, which we also installed. And you see here waypoint mode. And I can just give it a vector of points. And it would just start moving to there. So once you get this map, and I could right click and say add a point here, add a point here. You could draw your path, whatever, and you can find the most efficient for the most speed or whatever.
And now, does that algorithm also take into account like if you put an object in its way, or do you have to write that
Yes,
yourself?
it will take in because it will build a cost map. So if the object was in, so it's still doing this here. So I want to go from here. I'm putting the point A and B in here. But it will compute a trajectory, but it not necessarily be a straight path there. And it's constantly updating too. So say if it's moving and somehow a new object appeared here, and it's going to have a coordinate system set to do it here. And so does the cost here was 0? And so we say, oh wow, this got a big cost here. So it's still going to try to get to your goal point, but it's going to deviate either depending on if it thinks it's less cost to go here or less resistance to go here around that, and then continue on to the path there.
Now, how do you change like in code what it does when it sees an object? Like, let's say you want it to stop versus like trying to go around it or something.
It will. So as it's going through its poses, it will actually give feedback there too as well on the command. I haven't done it in a while. I've just been letting it do its own thing, but yeah, it should let you know. It tells you when it reaches the goal. It's going to send you a knowledge transfers back. So I don't and so you don't. This is a couple of things too of this lesson learned. So here's my map here. So this is where I'm at here. You just don't want to say go big. It will actually may actually work, but you really want to do, and then you got to figure out how often. But you really want to give it a lot of short goals, because it's going to give you once you get suggestions, it's going to say okay, reach. It's going to give you a reach goal, true status, and then you can just go to. I just have a loop of goals. So I make an array of goals and how to go through the goals there. But I try to break down it as much. If there's a straight path, I might just go here and then have it come here or something. But you had to figure out that increment, the task it needs to do. Because it also it can start deviating and it depends on the noise in the system here.
Right.
So that's one of the things you will have to figure out just about experimentation is figuring out how much goals you really need to get to the path after you get a map. And that's just trying it out. And if you see it it won't run into a while because it will see an obstacle. But if you get in the case of just starting to zigzag like that, then you might want to give it a little bit more help. It's going to get there, but it's going to take forever to get there.
Right.
Yeah.
Huh. I was just wondering if there's ways to fine tune it, because obviously one algorithm isn't going to work for all robotic use cases.
No, yeah. So it's really going to be like a lot of the parameters we could go through. That is like how big is that box, that the obstacle things there, and then because if you make it too tiny, it may not, and it will also say cannot reach goal. You try to compute it, and it would do a timeout for it as well too. And so you need to figure out those. It's not one. The algorithm could work for anything, but the parameters what makes the algorithm work for that environment.
Do you guys know anything?
I'm trying to finish what's up. I have a question for
Yes.
that as well. Do you remember, it was an issue I had last time, so probably not. When it's, like, when it goes to launch, what it's looking for. It's searching in a place for stuff to launch, right?
Yeah, so when you go to launch, like I'm on my computer here, so when some
Yeah.
we do our launch from this directory here, the root directory here.
But I think last time mine was looking in the wrong place for stuff, and when I updated, but I can't remember what I did to fix that. I can't remember what command that I either missed in your documentation, or
I think I recall where you asked.
I just can't remember the solution.
So you do a launch that says missing a file or something?
So like last time I figured this out, he's having the same problem. I believe this is the issue I had last time, where it's looking in a different directory. The launch file is looking for what I'm calling upon in a different directory.
I'll have a look at it.
Oh, is your file structure correct?
The file structure is exactly the same.
Let me see.
So
this is
if you look,
like if I run this, it's searching here.
found, whereas mine, when it does it, it looks through the red spot.
So you probably just need to do a source, the install. Did you just recently compile it?
We just built it,
Yes.
but we also have hit Foxy source again. Foxy source is gonna just run the source Foxy command.
Okay.
It's just an alias.
Okay. Yep, that's fine.
Unless I missed the alias, you could look at that.
Yeah, just make sure. So you just compiled it. Everything compiled fine,
Make sure I did this right.
and then
So, here, cd dot. So what it's doing is it's just let it go down right here. Come on.
yeah, mine does the same thing.
Source.
It's sources. that, but you also need to source the install directory, so that's probably why you didn't find the package.
Okay,
So
so go back in here, source the
Yep, so after you, for the first time, you have to do this.
source
No,
install.
you're in the right place.
Oh,
You're
okay.
there.
Uh,
Yep. CD, sim, and now source. Once you install it, you need to tell it it's a new package available, so source, install that setup, that flash.
Which one?
source space install
Install directory.
slash setup batch.
It's all.
Install. Don't put a space between that and the slash.
Yeah, it's the, let me see what you have there.
Cause I don't know.
And now try running that.
Do we need to build it again? Or
No, that's after you build. So you can always, every time you build, you can always run that just to be
wait,
careful.
I didn't run this after
Yep.
building.
And then yeah. And so you made a new package, it always installing the install directory, but it had no clue that it had a new update.
Okay, thank
And
you.
so that's what that does, it gives you,
I have a question compared to
Yep.
the speed and stuff.
What car is that?
What are I get that these speed like it's saying everything in meters per second and stuff.
Hello.
And what's this like turn?
It's not one wheel.
Is that angle? Is that speed?
yeah, that might be,
There's more old It's okay.
He's special, alright. Oh, there it is.
Just a slow.
yeah, it is
You know,
turning, I
just
don't
a big
know.
mover.
I kinda wish
that's
he stayed
setting
like
or
with the one wheel.
A little messed up.
in
I think
radians
it's
or,
Yeah.
you got
What's now?
Well, now I got something weird.
A virtual car.
Yeah, there's a. What is going on here?
That's what was Chris's question.
I just think this might be heading in radians.
I don't know what it's doing now.
I never.
but I was just wondering, like, I get that the car itself has a physical limitation,
Yeah.
but like, if I told it to go, you know, like 50 miles per
It's
hour,
better
would
than
it just try, like, does it know the car's maximum, like that?
No, I don't-
So much
Or, like, how does it know what
hanging out
PWM
with
this is?
It did have, in the
I
other
shouldn't have done a
code,
workshop
it did have a max velocity.
Or is that just for the simulator that I'm saying, or is that?
But the simulator, I don't think it
What's
does.
the first one before this?
If you had a 100-mile-an-hour power throttle,
Yeah, it's fine.
It's been a week.
yeah.
Whereas the car.
The
would
car
just-
records it would give you max RPM to the idle time. It does have a max velocity and it does scale.
I guess that's why it's gonna
Just-
Yeah.
okay.
End of day.
And that's written in.
But I don't think that's been in the
All my
simulator.
little.
Is that in the stat list that's scaling it?
Yeah, it's the parameters and max velocity. And you can down that too, so if you don't want to go full speed, you can make that max slower. So even if you feel it is not going, it's not saturating or something like that.
Okay. Thank you.
But yeah, I think the simulator has that.
Yeah.
Really,
Alright, let's see how fast we can get it to go.
yeah. So yeah, so you still. So the simulator is really good to get the algorithm, but it's not. If you're going to try to fine tune performance, then you want to go back to the real thing.
Right.
When do you leave for your trip?
Oh yeah, no, this thing can go fast.
Yeah, I figured you probably could. I'm gonna